In the last lecture, we had talked about the formalism of density matrix, which is useful for describing situations where we don't have pure states, but we deal with states which interact with environment, or states where we consider an ensemble, so that when you pick up a particular member out of that ensemble, that may be different from if you pick up another member. One of the things that makes quantum computing different from classical computing is the question of measurement. We have pointed out that when you have a situation where you have a superposition of states as an input and a superposition of states as an output, the output, though in principle it contains the results, or the, supposing you are calculating a functions so that the output could be function corresponding to several inputs at a time, because of the quantum parallelism which is inherent in such systems. The problem is that in spite of the fact that the information regarding the value of the function in this example that I gave you is there in the output register, when you actually want to extract this information, you cannot get all the information at a time, but you will get firstly only one of the results, but that's not the only issue. The issue is that you will get one of the random results out of that. Now this causes a lot of problem in quantum computing, and one has to really find a smart way of how to extract the information that you want. The question of measurement has always been a very central issue in quantum mechanics and quantum computing, and what I want to do today is to talk about the postulates of measurement. I call it the postulate because like other postulates, for example, that a state is represented either by a vector or a ray in the Hilbert space, or in terms of a density matrix in case of mixed states. The measurement is also a fundamental postulate, and what we will do today is to see what this measurement postulates mean. So let us define a set of what we call as a measurement operator. Suppose I have, in principle, I am making a measurement. It could be, for instance, of the energy of the system, any physical observable, the momentum, the angular momentum, or whatever you have. Now we have seen that when you make such a measurement, the system would, according to Copenhagen interpretation, collapse to one of the eigenstates. So let us assume that out of the possible results, so we have a set of operators which we call as the measurement operators, m, and let's put the index as small m, where small m gives me the possible results. Supposing there are n number of possible results, then m could vary from 1 to n. So this is the operator when we take the expectation value in certain states, then I will get a particular result out. Now according to the quantum postulate that we had, the probability of an outcome suppose I am talking about a particular outcome, m, well, whatever you want to, let's call it just m, the specific m, is given by this quantity psi mm dagger mm psi, where these mm and mm dagger, these are my measurement operators. Now since the only possibilities are these n values, so I must have sum over m equal to 1 to n, of course, dagger mn, that must be a resolution of identity operator. According to the quantum postulate, after you have made a measurement, and let us suppose you have got a specific m as a result of that measurement, the post measurement state is given by, now of course it is the measurement operator m which has acted on psi, and it is normalized because you are talking about a specific state. So this will then give you psi dagger psi. This is the state to which it will collapse after a measurement has been made. So this is basically our measurement postulate. Now what we do now is the following, that we look at what are the various types of measurement possible, and I will be essentially picking up two of them. The most important one is what is known as a projective measurement. Now remember, the completeness is there for any type of measurement because your measurement must exhaust, the list of measurement must exhaust all possibilities. Now suppose I make another demand that these measurement operators are actually orthogonal projectors. Remember, we talked about the orthogonal projectors onto the one-dimensional subspace of the relevant Hilbert space. And so instead of calling it mm, and since these are projectors, let's call them pm. So if these are the measurement operators, and these we call as the projective, also known as von Neumann measurements. Now firstly, the von Neumann measurements, of course I have hermiticity, so pm dagger is equal to pm, and I also have, remember that the projection operators are idempotent operators, so that pm square is pm itself. The reason is very obvious, that if you have once projected it, applying a projector a second time is not going to take it out of this space. So pm prime, this is equal to pm delta mm prime. See, if m and m prime belong to different subspaces, orthogonal subspaces, then obviously the result must be equal to 0. Now, so that along with our definition of what is the probability of the measurement, when we had said that the probability of measurement gives me expectation value of psi dagger mm, and since in this particular case pm square is equal to pm, so I get the probability of having a result pm is given by psi pm psi. So let us look at this specific case, because this happens to be the most common case that we normally talk about. Now suppose I look at a physical operator m, and this m we know has a spectral decomposition m pm, and we have just now said that this is m, these are the eigenvalues, and pm, which is their probability, is psi, actually I should have written like this, pm psi, this is the probability p which I wrote as p bracket m. So this quantity is equal to, if you rewrite it like this, psi sum over m pm psi. So you notice that this is nothing but the operator m itself, so therefore it is psi m psi. Now to illustrate what this actually means, let me give you a specific example of the projection operators. Let me talk about a 1 qubit state, and in that I have of course my basis state as 0 and 1. Let me define my measurement operator M0 as equal to 0, 0 and M1 equal to 1, 1. Completeness is obvious because 0, 0 plus 1, 1 is identity. And let me see what this measurement operator gives when it acts on an arbitrary state psi equal to alpha 0 plus beta 1. Let us look at this. What is the probability of picking up the value 0 out of the measurement? Now we just now said this is given by psi, the corresponding projection operator, which just happens to be psi 0, 0 psi. Now you can quickly calculate this because this is the bra psi, we have taken the ket psi to be given by this. So it is alpha star 0, remember alpha betas are complex numbers, plus beta star 1, 0, 0 and psi, which is again alpha 0 plus beta 1. So we can multiply this through and realize that the only terms that survive here are the product 0, 0 and so firstly this 0, 0 gives you 1 and the 0, 1 is 0. So if you just multiply it through, you will be left with alpha star alpha, and which is nothing but equal to alpha modulo square. And likewise you can show that the probability of getting the value 1 is beta square. Now suppose the result of the measurement happens to be 0. In that case, if result is 0, then what is the post measurement state? The post measurement state, according to our prescription, is then given by, remember, M acting on psi divided by the probability, that is square root of the probability psi M psi, and this we have seen operators M is corresponding to the state 0 is this alpha 0 plus beta 1, and this one we have just now calculated to be given by modulus of alpha square, square root of that is equal to modulus of alpha. And this one, obviously this scalar product is 0, so therefore I am simply left with alpha 0 divided by modulus of alpha. Now realize that alpha by modulus of alpha is basically a complex phase e to the power I phi 0. Now what this is telling us is that if my measurement gives me the result 0, the state 0, the post measurement state will be the same state 0 but for a global phase, but as we know that the global phase does not make any difference. So the state remains phi, the 0 state. A very special case of the projective measurement is when we make the measurement like this example that we gave you, where our measurement operators are M, M. Just now we gave the example of 0, 0 and 1, 1, and supposing this is in general true, these are the projection operators, where M's are the basis states. So these are the basis states. Now in that case, we say It is a measurement being done in a basis. All measurements do not have to be done in a basis, they could be in general in terms of any orthogonal vectors in the Hilbert space. So let me extend this idea to the case of multiple qubits. Well, we will not really do multiple qubits, but once we have taken care of 2 qubits, then the extension to other qubits, many qubits, should be obvious. But before I proceed for that, let me sort of explain how this situation would be. Supposing instead of measuring in the 0011 basis, I measured it in a different situation. Suppose I have the same state. I have alpha 0 plus beta 1, and we want to measure in a diagonal basis. See, this is written in what we call as a computational basis. So we have a state which is given in computational basis, whose basis states are 0 and 1, and I want to measure it in a diagonal basis, whose basis happens to be plus, which is equal to 0 plus 1 by root 2, and minus, which is equal to 0 minus 1 by root 2. Now, supposing I make a measurement of this state in this basis. Now, the job that I have to do is to first express my given state psi, which is expressed in computational basis, in the diagonal basis. And since plus is given like this, minus is given like that, I can express 0 as plus plus minus by square root of 2 and 1 as plus minus minus by square root of 2. Now, so I re-express these in terms of plus minus etc. so that my alpha 0 plus beta 1, that is my state psi, with a trivial algebra will be written as alpha plus beta by square root of 2 plus alpha minus beta by square root of 2 minus. This is the same thing re-expressed with this. Now clearly, if I now make a measurement, the probability that I get plus, the probability of getting a plus, is given by modulus of alpha plus beta absolute square divided by 2. And probability for getting the result minus is given by alpha minus beta absolute square divided by 2. Now, suppose my state is plus. In the same way, I can compute what is the post measurement state. You can simply compute m plus acting on psi divided by the corresponding probability which we have written down there. So, which is square root of 2 divided by alpha plus beta modulus, because this was square root of the probability, and you do the same algebra as we did earlier, and you will find that this is equal to e to the power I phi plus, which simply tells me that if the result of the measurement in the diagonal basis happen to be plus, the post measurement state, but for a global phase, will also remain plus. One point that you have to realize is, at this stage, if I made a repeated measurement in the same basis, since the state has already collapsed to a particular state, it will continue to be in that state. So, repeated measurement will not make any difference. Now, let me then make this extension to the projective measurement, but this time I will take the case of 2 qubits, which is a first step towards generalizing to n qubits. So my psi here is a general 2 qubit state, alpha 0 0 plus beta 0 1 plus gamma 1 0 plus delta 1 1. Now the point here is this, that suppose I wish to measure only the first qubit. Now notice this, that what is my operator corresponding to that? See, the first qubit's measurement, and suppose I am talking about the measurement operator corresponding to the situation where the first qubit is 0, irrespective of what the second qubit is. Now then my measurement operator corresponding to the first qubit being 0 is given by measurement operator where the first qubit is 0, second qubit is 0, measurement operator for first qubit is 0 but second qubit is 1. And this one obviously is 0 0, remember this is a 2 qubit state, so it is 0 0 0 0, and this one is 0 1 0. So if you add them up, what do you get? So you have got 0 0 0 0 plus 0 1 0 1. You have to remember that when I write 2 qubits in this way, the notation is this is standing for the first qubit and this one is standing for the second qubit. And likewise it is true for the corresponding bra as well. But you notice one interesting thing here. When I have written this, the bra, the ket and the bra for the first qubit in this term is 0. The ket and the bra of the second qubit in this term is also 0. But in this case, the ket and the bra for the first qubit is 0, but the second qubit in the second term is 1. So in other words, in both cases, my first qubit, supposing I have to now change the notation a little bit and wrote this as 0 0, okay, then you notice what I am getting is the following. So basically what I have done is to say that this is 0 0, which is this term, multiplied with 0 0 plus 1 1. So this is for the second qubit and this is for the first qubit, which is the same in both these terms. But this is nothing but a resolution of identity by completeness. So therefore, this term is 0 0, let me call it I2, meaning thereby this is the identity operator which acts on the second qubit. So therefore, what is my probability of getting first qubit as 0? The probability of getting my first qubit as 0 is, remember, so in this particular case, you look at what I will get, it has to be psi m0 psi. Now, since the identity operator is acting on the state, so basically what I have got is the following. Let me write it down. So I need psi m0 0 or m0 as we wrote it, 0, that's only the first qubit. And we have already seen that this is psi 0 0 psi. I have already given you the psi there, and you remember that this is the operator for the first qubit, and only my first two terms of psi, namely alpha 0 0 plus beta 0 1, had 0 in the first place. So therefore, that will be the only term that will survive, and a trivial algebra will see to it that this is actually alpha square plus beta square. Now remember that this is, I have assumed when I wrote down my first value of psi, I said it's equal to alpha 0 0 plus beta 0 1 etc., where the normalization was modulus alpha square plus modulus beta square plus modulus gamma square plus delta square is equal to 1. So this is the probability, and if you did the corresponding job for the first qubit being equal to 1, you will get this as modulus gamma square plus modulus delta square. So we have talked about von Neumann or the projective measurement, which is a special case of generalized measurement theory. What we will do in the next lecture is to tell you how to generalize it for the mixed case. How does one take care of von Neumann measurements for the mixed case, and then go over to another example of the measurement which is need not be projective or the orthogonal measurement.